welcome to AP Statistics. We're starting chapter 17, where we're learning about probability models. So far, the only probability model that we've learned is the normal model. And so there's a word picture to help you understand when you can use this model. Now we're going to use a little metaphor of a model rocket. This is a random variable, by the way. So, distribution X. So sometimes you have real world situations that are the outcome of a random process. Like it might be one of those things that you showed me the other day, Devin, where there's all of these, steel balls falling into like this grid of nails are falling down, and then they end up piling up in bins. We have one of these at the Museum of Science and Industry, where, have you seen this, where it's like you pour these balls down, and then at each nail they fall right or left, and then there's just a few that they're all being poured in the center. There's a few that go left, and make it all the way over to this bin. There's a few that go right, make it all the way over to this bin. But the overall pattern of the distribution of this random process is a bell curve. So that is, you're the one who was showing me that, right?
Yeah, I showed you the little like cookie thing.
So it's called a Quinn, I forget what it's called. But you can see these on the internet. It's like there's applets that make them go, but
you can search normal model toy and it'll come up.
Okay, so let's try that. Normal model toy.
Do you have one?
No, I was just.
Are they pretty expensive?
They are really
We should
expensive.
buy one for the class.
If you want to fund that, Lydia, go right ahead.
Yeah. The Galton board.
So,
I think
Galton
it's
board,
better.
okay. So on YouTube, so you can see these things, I guess, on YouTube.
It's like
And-
$50.
50.
And they sold out.
So it's a random process. You pour all these, there's a whole bunch of steel balls, and then this is a really nice sound. Well, maybe I should press this.
Ooh. Oh. This is a computer.
Well, it could
Reality
be.
is not conforming to your mind. Oh, there it goes.
The Galton board. It's like a rocket, a model rocket. Okay, so they release. Oh wow, that's fast moving. I didn't know that's reverse. Okay, so they pour them in. They can go left to right, but look, this random process can be modeled by a bell curve or by a normal model. The music is so pleasant; it's
It
relaxing.
makes you want to get one, right?
And it is logically possible that they would all end up in the far left bin. It's possible. Or they could all end up in the right bin. But what seems to happen over and over again, slow motion, is that look at this guy over here. Go. Yeah, I'm cheering for yes, he made it all the way over to this one, the far left. So it's like having a baby girl. It's gonna be girl or boy, left or right. So
20 kids and all girls.
so if you I love this. I should save this Galton board. Okay, I gotta remember that. I gotta show that to my fifth period class. Thank you, Devin.
You're welcome,
Devin, that's
Mr.
awesome.
Royce.
So
Yeah, Devin.
okay. So when you get a distribution of a random process that piles up in a bell curve that is unimodal and symmetric. Again, this is an HIST, histogram. If you have a histogram that's unimodal and symmetric. And outliers, what's the outlier situation? Outliers, none. Then you have satisfied the conditions of using a normal model of the distribution of this random variable x. So this random variable x is to distribute. So the question is, what would the definition of random variable x be? I guess the definition of x would be the bin in which the metal ball ends up. and there's a distribution of those, and this is a histogram that shows the distribution of all of them in any particular pouring of the Galton board. So it turns out that this normal model is not matching reality exactly, because as you could see, some of those bins had more than they were allowed to have according to this, they just had to conform to this model. But the model is a pretty good description. And that model tends to have a mean mu sub capital X and a standard deviation, sigma sub capital X. And the formula for that mean, the middle is found by taking the X bar symbol, which is sigma X sub I over N. We add up. Oh, you know what? I want to write that a little bit differently. Time out. I mean, that's not what I wanted. I wanted sigma X sub I in the numerator, sigma X sub I, and then divide the whole thing by N. That in third grade, that's how you learned how to average a list of numbers. You added a sigma X sub I, you added up all the numbers, and then you divided by the total number of numbers.
Yes, sir.
Which, by the way, you'll have the green sheet when you're doing the script, the word picture quiz, and this is like Formula 1 on the green sheet, so that one you can just copy down. Also, the standard deviation of the normal distribution is also on the green sheet, so you'll just be able to copy down. It's 1 over n minus 1. We used this formula in Unit 1 back in first semester. And take x sub I minus x bar quantity squared. Reminds us of a formula that we did on today's quiz, kind of similar. Standard deviations tend to have square roots in them, and they tend to have deviations squared. So, no surprise that that was on today's quiz. Now, by the way, there is another way. It says or something else. These conditions for launching this model are metaphorically comparable to a process that happens down in NASA when they decide that they want to launch a rocket or a space shuttle. Now, back in 1986, it was about this time of year, late January of 1986, the Space Shuttle Challenger exploded. It was the day of the State of the Union address delivered by President Ronald Reagan. He's president from 80 to 86, roughly.
That's my favorite president, Mr. Royce.
Pretty good president. Now, what's going on here with that? These models of reality, they're comparable to model rockets. Like rockets, you shouldn't go launching rockets carelessly. A lot of different models, just like there's a lot of different model rockets, and just like the space shuttle was kind of like a rocket, they kind of rocketed up into the atmosphere. When you look at a normal model and use it, it's kind of like launching a rocket. When you go to your calculator and find the normal CDF command and say, I want to know what normal CDF from -1 to 2 is, once you press enter, that's comparable to pressing launch. You're saying, I think we're cleared to launch. Now, that was my second year teaching, 1986, January 1986. Yeah, it started in September of 84, so 84, 85. That's my second year teaching. I was teaching at Naperville North High School. And when the Space Shuttle Challenger exploded, I was supervising a study hall in the library over at Naperville North. And it's one of these things I'll remember for a really, really long time, like as long as my brain is properly functioning. And that is that the chemistry teacher, really big guy, he comes bursting out of his classroom into the library, and he announced to everyone in earshot, he said, the Challenger exploded. Sure enough, it's a big day for education because it's the first teacher in space. What was her name? She was on the space shuttle. She died that day. And they had a line written into the script of the State of the Union address where Ronald Reagan was supposed to say, and today, our space program put the first teacher ever into space. But they shouldn't have pressed the launch button because the conditions for launch were not satisfied. It was too cold. The conditions for launch were that it's got to be 57 degrees Fahrenheit or warmer. There were icicles down there in Cape Canaveral, Florida that morning. It was an unusually cold day in the south. It was January. But why did they press launch? Why did they launch the rocket?
They wanted the cloud.
Maybe they wanted, we don't know, maybe they wanted to be able to put that line into the State of the Union address, and there might have been political pressure. We don't know. That's a tough investigation. We know the O-rings failed. The O-rings were produced by a company in Illinois. It was like Morton something. They had to change their name after this. It was like such a splotch on their reputation. In fact, the son of the guy who ran that company went to Stevenson High School. So it was a rough year for that kid. But, you don't want to press launch. You don't want to use these models. Don't launch the model. Some years I show this video from YouTube where, see, that day, the parents of that teacher, she's going into space. Her parents were there. They had these stands set up for people to sit, like stadium seating. And someone put the camera, they had the camera the whole time on the parents of this teacher. So it's really, I don't show it anymore because no one really wants to watch parents watch their children die. No one ever really wants to see that. But that just kind of drives home the point emotionally. When we talk about the conditions for launching these models, don't use a normal model unless, check, unimodal, check, symmetric, check, no outliers, check. Okay, now we can use the normal model. Don't put people through the consequences of launching a model when it's not justified. Sometimes instead of a histogram, sometimes what they'll do is they'll show you what's called an NQP. And that's not going to be on, well, you can just write NQP, but for your information, just put some notes down here because there's all these acronyms. When you see NQP, that's an acronym for normal quantile plot. And you don't know how to make a normal quantile plot, they're just going to show one to you. Sometimes they call it a normal probability plot, normal probability plot. But the point is this: if the normal probability plot is straight, then the underlying distribution from which this plot was constructed is unimodal and symmetric. If the normal quantile plot looks like this, if it has that kind of a curve into it, then you can take some string and put the string at the beginning of the plot and just spread it out. And if the string, calculus students would call this a tangent line, but if the string, the tangent line, is below, if the string ends up below the curve, B-L-O-W, then the underlying distribution is not symmetric, it's skewed left. And the third case is a normal quantile plot that looks like this. And when you put the string on it, just put the string at the left of the curve and stretch it out. And if the string, sometimes we call this the string test, but it's just a tangent line. If the string is above the normal quantile plot, then that's a signal that the underlying distribution of random variable x is skewed to the right.
Wow.
So, just so you know, there's different ways to check. Like if you're going to launch a space shuttle, you should bring out a thermometer and check to see, is it 57 degrees Fahrenheit or warmer? Otherwise, don't launch. If you're going to launch the normal model, think of a model rocket. Have you ever launched a model rocket? Maybe when you were a kid, you would take model rockets out and launch them. You were getting ready for today in stats. That day was important in your development.
Did you go down?
I did do that.
But there's conditions for launch. You make sure that there's all the little children, maybe the chipmunks and the squirrels are far away. You don't want them to get hurt. You want this to be a fun day. You don't want to end up in the hospital. So instead of bringing out the thermometer to check the temperature, you bring out the normal quantile plot, and then take out your string, find out, straight, then. All right, now, there's another type of model of random variables that we're gonna use today that sometimes the normal model doesn't work. Sometimes we use the geometric model, and that's what we're gonna learn about today. So join me now in this lesson on probability models, and we're gonna learn about the geometric model. So in fact, there's two word pictures. We're gonna learn two new word pictures. Word picture number 2 is based on the letter G, not the letter N for normal, but G for geometric. And we're also going to learn word picture number 6, which is based on the number 2. These are mnemonic devices. And if you have a photographic memory, then this word picture quiz will be really good, because all you gotta do, some people, I hear this from time to time, people who have a photographic memory, they just look at the page of a book and then they look at the next page. And during the test, all they have to do is page through the pages, and then they can ace the test. You might have a photographic memory to some extent. Probably everyone does to some extent. Hopefully what will happen is having the conditions for launching displayed visually might help you remember them. Otherwise, what are you doing? You're just memorizing lists of information.
Yeah.
Really, is that what you want your life to be? No. You want to look at pictures. You don't want to memorize lists. Some people do want to memorize lists, in which case, fine, go ahead and memorize the list. But we're still going to give you the word picture quiz to see how you do. We're going to put it in the grade book. All right, so these are the 2 new word pictures we're going to learn. I would argue that you basically already knew the information for the normal model. This was stuff you knew already, where we just kind of put it into a picture. All right, here we go. Well, there's some vocabulary here. Bernoulli trials and that kind of thing, but I'm going to introduce our new material in the context of a real world problem, and we'll call it problem 1. So let's just try to squeeze problem 1, which has parts A, B, and C. And after we get through parts A, B, and C of problem 1, I think you will have a pretty good idea of what Bernoulli trials are and what a geometric probability model is. So here we go. Let's go to a real world math problem that uses both Bernoulli trials and the geometric probability distribution. All right. We're in the real world of rolling a 10-sided dice. We are going to roll a 10-sided die. 3 dice, 1 die. Normally a die has 6 sides, but this die has 10 sides. You roll, it has numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going to let random variable x represent or equal the number of Bernoulli trials. So I have to teach you what a Bernoulli trial is. Bernoulli trials until the first, that's a key word in Bernoulli trials. It's a key word in geometric probability. Until the first 8 appears. So we're just going to keep on rolling the die until the number 8 comes up. Now, what is a Bernoulli trial? A Bernoulli trial is a particular type of random event. It's a random event in which there are 2 possible outcomes. And that's what the number 2 is in red in word picture number 6. If you want to take notes simultaneously on the word picture quiz, number 6 on the word picture quiz is a big 2. A big number 2. So put that down in number 6. Okay. And whenever you roll a 10-sided die, in fact, there are only 2 possible outcomes. Every time you roll the die, it comes up as either an 8 or not an 8. So there's a lot of situations that seem like there's many possible outcomes, but you can verbally frame it as if there's only 2 possible outcomes. Like every day, there's only 2 types of weather. There's days where there's some snow and days where there's no snow. It's only two types of days when it comes to weather. It's either snowing or not snowing at some point during the day. There's only three types of people: those who can count and those who can't. So just keep that in mind.
That was a good joke, Mr. Linus.
That was good.
Did I tell that last year?
You told the last year.
Or was it 2 years ago? Was it 2 years? Did I tell it to you? Or,
Or 2 years ago.
2 years ago. I'm sorry. So, but yeah, so there's only two possible outcomes. So that's what we have here. Now the probability of success is constant. We put, that's the green part of Bernoulli. Probability of success is constant for all outcomes. Now, what's the probability? Suppose success is defined as rolling an 8. What's the probability of success the first time you roll a die? 10%, 1/10. The probability of rolling an 8 the second time is still 1/10. It's constant. So under the 2, in your picture, we're artists today. Switch to the green paintbrush, pecan. Just put pecan under there. That's just a little reminder. P, which is the probability of success, has got to be constant. And you can put that on the word picture quiz also. Now, the third requirement for trials to be Bernoulli trials, and by the way, when a ball drops out of one of those, what is a Galton board, on a Galton board, there are like not just two possible outcomes, there are like, I don't know how many bins there were, maybe like 18 bins. There are 18 possible outcomes. The outcome of that ball, there are the 18, so those were not Bernoulli trials. Or you could set it up as Bernoulli, it's either falls in the far left or not the far left. So the probability of success has to be constant for all outcomes. So it's like the probability that it lands into that far left bin is probably the same for every ball, and they're either independent or not independent. So is the outcome of each roll of a 10-sided die independent of what the previous outcome was? Yeah, so it's independent. Now there are some safety nets here. If you can't prove they're independent, or RS is just an acronym for representative sample. So I will state that up here. RS stands for representative sample. So sometimes you can't, it's hard to argue independent, so we go representative sample instead. And sometimes there's also a safety net on pecans, because sometimes it's not exactly constant. Sometimes it changes a little from trial to trial. So there is an or here. If it's not exactly constant, 10 little n is less than big N, where little n is the sample size and big N is the population size. So we'll see that today. So here's the whole word picture. On next week, probably be Friday, I'll give this quiz. Next week, what you're gonna have to be able to pull off is for problem 6 on the word picture quiz, you're gonna have to be able to write 2 possible outcomes. The probability of success is constant. Or if it's not, then 10 times the sample size has got to be less than the population. Then the third condition for Bernoulli trials is the trials have to be independent, or if you can't argue that, at least argue that it's a representative sample of whatever it is are in the trial. So there it is. There's a red, green, and blue part to the picture, somewhat artistic. It's just a mnemonic device for remembering the components of the Bernoulli trial. By the way, when you roll a 10-sided die, those are Bernoulli trials because there's 2 possible outcomes, 8 or not 8. The probability of success is constant and the trials are independent of each other. Okay, so now part A, here's a question. What do these models look like? You can look at a model graphically, or you can look at the model in a chart. This chart has no right boundary, it's infinitely long. And just like the normal model has to be represented with a number like 5, maybe mean of 5, standard deviation of 0.2. It can be represented graphically. get a z-score of 0, 6 might have a z-score of 1 divided by 0.2 is 5. And so we could find the area under curve. So usually the graphical representation of a normal model is something that looks like this. A geometric model can be modeled by either the letter G with the probability of success, or it can be modeled graphically with an infinitely long chart, probability of capital X equals lowercase x. So usually for a geometric model, instead of using this kind of graphical representation, we use this kind of graphical representation. But that's just, okay, so let's write down what is the graphical representation of G of 1/10. And then I'll let you decide whether you want to use the orange representation of the model or the green representation of the model. Because it's not both and. On the AP test, they let you get away with either orange or green. The orange representation is G of 1/10. Here's the green representation. Get ready, hold your breath. Lowercase x. Probability of capital X equals lowercase x. And it could be,
Stylus.
good thing we have a floor in this room. I know you don't believe it, but because it doesn't show up on the camera. But trust me, you just gotta trust me on this. There is a floor. It could be that the number of trials until we finally get an 8 is 1. What's the probability that the first success is on the first attempt? 1 out of 10 is your answer over there. That is correct. It could be, though, that the first 8 shows up on the second attempt. Raise your hand if you think you would like to take a guess as to what is the probability that the number of Bernoulli trials until we finally get an 8 is 2. What's the probability that the first success is on the second attempt? Think you know, just raise your hand. I might call on you. If I do call on you, be prepared to say what your answer is.
It's got a lot of options.
Does anyone want to give it a go? What's the probability that the first appearance of a number 8 is on the second attempt? Who's pretty sure they don't know? It's like, man, I don't know. You could probably do a tree diagram. I'll give it a go. Now, if I understood your question correctly, you asked, is it 9/10 times 1/10? Is that what your question was? Now, actually, yeah, you could arrange it on a tree diagram, like the first attempt is either success 1/10 or failure 9/10. And then the second attempt would be either 1/10 success, 9/10. So yeah, actually it is, the first branch would be failure, upper branch would be failure, 9/10, times the lower branch would be success, 1/10. Yeah, so it's 9/10 times 1/10. The probability that the first success, this would be like a leaf where the first 2 branches are failure, so 9/10 times 9/10, or 9/10 squared, times 1/10. Now, would you please fill in the probability that the first 8 appears on the 4th attempt? Raise your hand if you think you know what that one's going to be. All right, Devin, go ahead.
9/10 times 9/10 times 9/10 times 1/10.
Yeah, so 9/10 to the 3rd times 1/10 is correct. And what these tables, they're infinitely long because there's no guarantee that you'll ever get an 8.
Yeah.
So it's go ... and then put the letter K, it's a lowercase k, and then ... forever. So we need a formula for the probability, this would be the probability that capital X equals lowercase k. And that's kind of like the general formula for all of these cells. Who thinks they've got it? In terms of k, what's the probability that the first success is on the kth roll? Dan, do you see if there's kind of a pattern that you might be able to see a pattern that shows a relationship between this number and that number?
3, you have a K isn't,
It's 9 tenths to the k minus 1.
Wait, I think I heard it. Say it one more time, just a little bit louder.
It's 9 tenths to the k minus 1.
Yeah, so notice that the exponent on 9 tenths is always one less than that number, so it's 9 tenths to the k minus 1 times 1 tenth, then dot, dot, dot. Okay, there it is. So, if you decide to press launch on the geometric model, then you need to document which model you're launching. You can document that either in orange
I like orange.
or in
I
green.
think orange is.
Because every time you write orange, it means this, which amazingly is an infinitely long table. And guess what the sum of all of these cells is? If you were to add them all, an infinite number. It's an infinite series. What is the sum of all those probabilities?
0.
1 over
It's one. It's one. Just one. It's not the G. It's actually, it is a geometric series. Okay, over 1 last time. So the first term is 1 tenth over 1 minus 9 tenths. 1 tenth over 1 tenth is 1. So that's an infinite, it is an infinite geometric series.
This is count
But-
2.
But that's, so, which actually, that's a pre-calc problem. That's a that, once you get into non-geometric series, then you have to use calculus, use calc BC. But it's actually algebra, or college algebra is the first place you see an infinite geometric series. But the point is that you have to report out which model you're launching or utilizing. Launching is not the official mathematical word there, but we're just using that as a metaphor.
Is it like club or football?
Yeah, oh yeah.
Or
Big time like those. So anyway, so let's do parts A, B, and C. So far I've just given you the given information for problem 1. Now let's do parts A, B, and C. Are you ready for this? All right, here we go. Part A. Find the probability that the first 8 is on the 20th roll. So without a calculator, I'd like you to write down what you think the probability that the first success is on the 20th attempt. Let's give it a go.
I'm gonna go with
Okay.
yeah.
I hope that you focused in on this formula with, basically you're looking at K is equal to 20 in the probability that capital X equals K is Q to the K minus 1 times P, where Q, by the way, is always the probability of failure. P is the probability of success. Lowercase p is probability of success. 1 minus p equals q is the probability of failure. Epic fail. Okay. So instead of like 9 tenths is 1 minus 1 tenth. So that's q to the k minus 1 times p. So we want to find the probability that the first success is on the 20th attempt. Hopefully what you did was take 9 tenths to the 19th power times 1 tenth. By the way, on your calculator, let's round that to 4 decimals. Do me a favor, take 0.9 to the 19th, that's 9 tenths to the 19th, times 1 tenth. We're talking, hey, it's really not that unusual. It happens 1.35% of the time. 0.0135, here we go, approximately 0.0135. That's part A. Any questions on how to find the probability using this geometric model? It's not a normal model, it's a geometric model. Find the probability that the first success is on the 20th attempt. By the way, back to word picture number 2. Let's go to the word picture quiz. Here's the answer to problem 2 on next Friday's quiz.
Yes.
The answer to problem 2 is, in order to launch this model, the conditions, there's 4 conditions. 1 is you need Bernoulli trials, which means, so if you know the answer to problem 6, just export problem 6's information into this. It's even color coded. There has to be 2 possible outcomes. The probability of P, probability of success, has to be constant, or if it's not, 10 little n has got to be less than big N. The third condition on the checklist, hey, are we ready to launch? No, don't launch. This could really be upsetting. This could be an epic fail unless we check all 4 conditions for launching this model. The trials have to be independent, or if that's hard to argue, then use the representative sample safety net. Then here it is, the 4th condition, don't launch the geometric model unless you first of all check to see whether or not first is the primary feature of the problem. Is this one of those problems where they're looking for the first success? Sometimes it's a fixed number of successes. Like, what's the probability that we end up with 5 of those little Galton board steel balls over in the far left-hand bin? You know, a fixed number of successes. We could look at the probability that the first ball in the far left bin is the 20th ball dropped down. You know, sometimes we were concerned about the first success, sometimes we're concerned about a fixed number. These are the 4 conditions. So it turns out that the parameter here, or the only thing, you don't need 2 numbers, you don't need a mean and a standard deviation. In order to specify a particular geometric model, all you need is the probability of success. And what is the average number of attempts until the first success? Well, tell me this. When we roll the 10-sided die, what would you expect the number of attempts until the first 8 would be on average? Like, sometimes it'll be less than average, some bigger than average, but what do you think the average number of attempts is until an 8 finally pops up? I mean, what does your gut tell you? Did you say, what?
You're wrong.
Did you say 10?
I said 10.
You're
10
wrong.
is actually correct. You would expect, since the probability of success is 1 out of 10, you would expect, see, it's 1 over P. 1 over P is the mean. 1 over a 10th is 10. Suppose you have a coin. What's the average number of attempts until the first head? It's 1 over 0.5, so it's 1 over 1/2 is 2. So you would expect to have to toss a coin twice on average to get ahead. Sometimes it'll be more, sometimes less, but on average, so it's, and then, yeah. So, I mean, that's fine. That's a formula that you're responsible for knowing. Now, in terms of the other formulas, is Val. Val came up with the probability of capital X equals lowercase k. That was her formula. She said it was Q to the k minus 1 times P. So that's the formula for filling in any given cell in the distribution. The standard deviation you're also responsible for. This is not on the green sheet, but it is Q over P squared. Doesn't show up a lot on the AP test. It could, you're responsible for it, but it's actually unlikely that you need it on the AP test, but you do need it for next Friday's word picture quiz. So there it is. Word pictures 2 and 6 are the word pictures for today. Q over P squared, where Q is the probability of failure. Yes?
Who was Bernoulli?
Oh yeah, so thanks for asking. So Daniel Bernoulli, I mean, what do you have to do to get a mathematical process named after you? Daniel Bernoulli, he came from a family of mathematicians. His dad plagiarized his own work. He was a better mathematician than his dad. So when he found, so he puts all his time to making the book. It's not like an e-book. This is back in the 1700s. So, so he publishes his book. His dad's jealous. Dad takes a manuscript, publishes it under his own name.
That's illegal.
But he still did it. I don't recommend doing that. But one thing Daniel Bernoulli did that's really remarkable is that and the story I'm about to tell you has an element of goriness to it. I'm not going to try to be super graphic, but if you tend to get squeamish when people are talking about medical situations that involve blood.
I do, yeah, I will pass out.
Okay, then okay, seriously, if it's a pass out risk, okay,
It actually is.
go ahead and step outside, because this is one of those stories.
He's actually really bad at that.
No, and that's why I give the trigger warning up front. So, you can have a seat, or just go ahead and have a seat in the library, we'll come get you. It'll take about 2 minutes.
Like, he almost passed
2
out
minutes.
and stopped blood once. I'm not joking, yeah.
Okay, so Daniel Bernoulli made an amazing discovery that helps us today. It helped us discover how to design airplanes, how to make airplanes fly. But he made this discovery during a vivisection. A vivisection just seems wrong to do these things, but it's when you dissect a person while they're still alive. And a lot of medical discoveries in the 1700s were made during vivisections. Daniel Bernoulli was attending, he was a doctor, he was attending a prison vivisection. What they would do is they would take people who are on death row. They figure, well, you're going to die anyway. Why don't we just dissect you and learn something? That can be your contribution to humanity. We're going to learn something about medical science. And during a vivisection, they sliced this guy open. And he made an observation. As a mathematician, you could tell there were like spurts of blood that would go really high and then not as high, really high, not as high. So he basically discovered the difference between systolic and diastolic pressure. But more importantly, if you take a look at the way airplane wing is shaped, when there's not a flow of blood, but you have top of the atmosphere, but it applies to airflow. So when you have airs or like vectors going above, it's like they're squeezed above and then down below. Well, it turns out that guess when the air is moving faster? Is the air that's just going below the wing? Just like there were two speeds of the blood was flowing when it was spurting out of the guy's arteries. Some was going faster, going higher into the air, some was going not quite as high. Is the air that's going above the wing traveling faster or slower than the air below the wing? It's actually going faster. When it goes into a narrower channel, think narrow blood vessel, it's a faster speed. Here it's slower. And so the channel is narrower. It's not narrower here, it's just normal. But then the pressure, what happens when the fluid's velocity is faster? Do you think the pressure is increased or decreased? Higher velocity, it's actually, the higher the velocity, it's counterintuitive, it's actually less pressure. So this is the Bernoulli, what, I'm sorry? So, and Val is just contributing that, I think that's, does anyone have my phone? The pressure for PV equals nRT is on my phone, right? It's very top equation on my phone is PV equals nRT. Let's put it right up on the camera. PV equals nRT. There's a lot of equations on there. But Val has indicated that she believes that PV equals nRT, pressure inversely related to velocity. So V is a velocity. And so P equals nRT over velocity. So when velocity goes up, pressure goes down. Thank you for helping me understand my cell phone cover. So this is pressure decreases. So you have lower pressure, because the higher velocity, you have lower pressure above the wing. That creates lift, and that's the force. There's four forces in airline science, in airplane science: thrust, drag, gravity, pull of gravity. Now, lift is what lifts the airplane. And Bernoulli discovered this principle during a vivisection. Please don't go around cutting people up, especially if they're alive. I'm just going to pause until we